Hello everyone. Welcome to this session on state space models, abbreviated as SSMs. A large amount of data that is processed is sequential in nature. For instance, the language, natural language that is obtained as text, which forms the fundamental basis for foundational models, are all sequential in nature. So we saw what sequential data refers to in the previous sessions. Now, modeling sequences, especially the longer ones, is extremely important while considering these kinds of scenarios. Transformers have been the go-to choice for modeling this sort of sequential data, given their applicability in multiple domains. However, if the context length, as it is called, or the length of the sequence grows, the amount of computation that is needed in transformers grows quadratically as the length of the sequence grows linearly. So why is this? If you recall how transformers operate, to process every token, one needs to compute the attention scores with all the tokens that are there in the sequences, and this has to be done for each of the token, which means that if there are capital L number of tokens in the sequence, then it takes OL squared computations to perform both training and inference. And therefore, when the length of the sequences become too large, then the computation required for transformers becomes prohibitively large. To address this issue, the community has considered an alternative model family called the state space models, in which the computation that is needed for training and inference does not grow quadratically as the sequence length increases linearly. Now, let us look at how is it defined mathematically. An SSM is defined by the following equations. So for now, let us consider the input and the output sequences are both one-dimensional. So suppose u of t and y of t represent the input and output sequences represent respectively. And output sequences respectively. So let's say u of t and y of t represent the input and output sequences respectively. Now both of these are unidimensional. So this will make the algebra easier. So later in the session, I will discuss about how to extend this to multidimensional sequences. Let's say that we have an input sequence represented as ut and yt represent the output sequence, and both of them are one-dimensional signals. Okay. Now with this, SSM is defined as follows. And just remove this. So given that we have a one-dimensional input and output sequence, SSM is defined as follows. So x dash of t is a times xt plus b times ut, and y of t is equal to c times xt plus d times ut. So this is the definition of a state space model. For those of you who are familiar with the classical control theory literature would readily recognize this as the classical one-dimensional state space model that is defined to handle dynamical systems. Now, this is the definition of a state space model where xt is an n-dimensional hidden space vector, and A, B, C, D are the learnable system parameters, learnable system or model parameters, let's call them the model parameters. Okay, so this is the definition of a state space model, and x dash denote the temporal derivative, denotes the time derivative of x. Okay, now this is the definition of a state space model. What we have is, given a signal u of t, which is one dimensional, call it signal or a sequence. Now that is first projected, so to speak, onto a state space or a latent space, which is n dimensional, denoted by xt. Now dynamics are learned, the temporal transition dynamics are learned on the state space. Now what we are saying is this, the first equation here governs or models the evolution of the state space across time, and that is modeled using the A and B vectors or matrices as the case may be, and the output y of t is connected to the state space through the matrix C. Okay, and the vector or matrix D connects the output to the input ut. Now, it is not difficult to see that this has similarities with the recurrent neural networks, okay, where the difference is that in recurrent neural networks, the relationship that governs the dynamics is nonlinear, whereas in a linear state space model or a state space model, the relationship between the state dynamics and the outputs is governed by linear equations. So now axt plus but and cxt plus dut, all of these are linear relationships, and that's how it differs from a typical recurrent neural network that has nonlinearities connecting these quantities. Okay, now throughout our discussion, unless otherwise specified, we assume that u and y, which are the input and the output sequences, are both one dimensional. So as I said, I will discuss how to extend this to multi-dimensional input sequences as we move on. Okay, now these A, B, C and D are the so-called model parameters that would be learned via gradient descent. Now this is the definition of a state space model. In the literature, typically this D is not considered. Let me just write it. Typically D vector or D matrix is omitted since it can be realized via a learnable skip connection. Learnable skip connection. So if you closely look at it, yt is given by c times xt plus d times ut. If ut is the input, all we are doing is we are taking the input and multiplying it with a matrix D, and that appears in the equation of the output, which is nothing but saying that there exists a skip connection from the input ut to the output uh, yt without considering the intermediate state space xt. However, a typical skip connection would not have any multiplication factor, but you can always have a learnable multiplication factor. So, since this can be learned via or realized via a skip connection, this is not considered while defining a typical state space model. Okay, so D is out of the equation now. Okay, now with this, the final SSM, final continuous time SSM, I would say, state space model is given by, so we have x dash of t is a times xt plus b times ut, and we have yt to be equal to c times xt. This is the equation of a state space model in continuous time. Okay, where a, b, c are the learnable model parameters, where a, b and c are learnable model parameters. Please note that I said that this is for the continuous time signals. So we are assuming that u and y and therefore the x are all continuous time signals, and therefore the derivative of x is well defined. So I can write it as x dash of t, where x dash of t is the time derivative of x. Okay, but in practice we will not have continuous signals. So, for instance, if you take the sequences of language, natural language, the text that we get, the language data that we get is not continuous in time, because we have sampled the time, and what we have is a discrete sequence. Now the question is, how does one rewrite or convert this continuous time state space model into the discrete time version is the question. So let us take that question now. So the first step in applying SSM to sequences, or let's say discrete sequences, is to discretize the model. So what is meant by discretization? One needs to go to the classical signal processing realm. Suppose you have a continuous time signal. There are multiple ways to discretize it, one of which is sampling. So what is done is that samples of the signal are considered at discrete times. Now once the signal is sampled, the underlying state space equation will change corresponding to the type of sampling that is being considered. So let us look at what happens. So suppose we have a discrete input sequence given by u, which is equal to u0 comma u1 u2 and so on. This is the discrete sequence that we have, which is obtained by discretizing ut. Discretizing u of t. Okay, now which means that you k, which is the kth discrete sample, is u times k times u of k times delta, where delta is the step size. What is meant by this is that suppose we have a continuous time signal this way. If this is a continuous time signal and this is t, to discretize this, let's say that this is u of t. To discretize this, what one would do is consider samples of the signal at discrete time steps, and the difference between these two time steps is what is called as step size or delta. So this is k equal to 1, k equal to 2, and so on. And at every step, what is considered is the value of the signal at that particular point. So we have, this is u of 1, this is u of 2, and so on. So this would be u0, this would be u1, this would be u2, and so on. So this is how one would discretize. Once the input signal is discretized, the underlying state space model also gets altered in the sense that the forms of the ABCD parameter matrices that are there in the state space equations would get modified, and those will become functions of the time step delta. Now, the way they get transformed depends on the type of discretization that is employed to convert the continuous time signal into discrete time signal. Multiple methods use multiple ways of discretization. I'll just show one of such methods that is often used in most of the state space model, called the bilinear transform or bilinear method. It's also called the Tustin's method, where people who are aware of signal processing would identify this, where the idea is to convert the signal from the continuous Laplace space to a discrete Z transform space, right? So that is the idea of Tustin's method. I'll not go into the details of how the bilinear transformation method works. However, it is sufficient to note that after discretization, the SSM parameters change as follows. Now let's call them as A bar. So discrete parameters are A bar. So A bar now becomes I minus delta by 2 times A inverse of this times I plus delta by 2 times A, where I is the identity matrix of appropriate size and delta is the step size as we saw. So B also get transformed into I minus delta by 2 times A inverse delta times B. So this will be B, and C, that doesn't change, so it will just stay as C bar will be just same as C. Now here I is the identity matrix of the appropriate size, and delta is the step size used in discretization, is the step size used for discretization. This is called the Tustin's method or the bilinear transformation method, where the state space model gets transformed from ABCD into A bar, B bar, C bar. C bar just remains same as C, and while A bar and B bar becomes a function of the A and B that were there in the continuous time counterpart and the step size delta. Okay. Now with this we have a new set of equations. So for SSMs for discrete sequences, looks as follows. So suppose we consider state space models for discrete sequences. Instead of having x bar, we have xk, that is equal to a bar times x k minus 1. Note that instead of derivatives, now we have first order differences, plus b bar times uk and yk, which is the kth token in the output sequence, is equal to c bar times xk. So this is the new state space equation that we have. The above equations define a sequence to sequence map instead of a function to function map. In the continuous time state space models, what we had was a mapping from a function ut to another function yt. Here we have a sequence to sequence map from sequence uk to a sequence yk via the state space xk, right? So this is exactly what we have. So this is the basis of all the modern day state space models that are employed in practice. Okay, so just to recap, what did we do was we started from the definition of state space models, assuming that the signals, the underlying data that we have is continuous. Now, since in practice we work with discretized data, we discretize the continuous state space models, obtaining the discretized state space equations, discrete state space equations with appropriately defined A, B, and C that is governed by the underlying discretization method. Okay. Given this, the next goal is to come up with a method that would enable us to find A bar, B bar, C bar via training. Okay, so now how do we obtain A bar, B bar, C bar given some data is the next question that we are going to answer. So let's write training discrete SSMs. The question is, how does one train SSMs given data? Okay. Now, what can be observed here is that these equations define a recurrence between the previous states and the current state, and this recurrence is effectively used to come up with algorithms that are computationally efficient while training SSM. So let us look at that. Suppose or assume the initial state vector to be 0. So this is just a model assumption that is made for convenience, which means that we assume x minus 1 to be equal to 0. Now then with this, unrolling the state space model leads to the following recurrence. Let's write that down. X naught will be equal to B bar times U naught. X1 will be equal to A bar B bar times U naught plus B bar times U1. We have X2 to be equal to a bar squared times b bar times u naught plus a bar b bar u1 plus b bar times u2 and so on. So we can write this recurrence for xk, and similarly y naught will be equal to c bar b bar times u naught, and y1 will be equal to c bar a bar b bar times u naught plus c bar b bar u1. Y2 is equal to c bar a bar b bar u naught plus c bar a bar b bar u1 plus c bar b bar u2 and so on. So what I just did was plugged in particular sequences x1, x2, x3 here and expanded this via unrolling. Okay. Now this can be generalized as follows. This implies yk is equal to c bar a bar to the power of k times b bar times u naught plus c bar a bar to the power of k minus 1 times b bar into u1 so on up to c bar a bar b bar u k minus 1 plus, let's just drag this a little, plus c bar b bar u k. Okay. Now if one closely observes this looks like an equation that is familiar to, an operation that is familiar to us. Suppose k bar is an L length vector, okay, given by the following. So c bar b bar, c bar a bar b bar times c bar a bar to the power of L minus 1 times b bar. So if we define k bar to be this, an L length vector to be this, then it is easy to see that yk, which is the kth element of the output, is simply given by k bar times the convolution, k bar times the convolution, or k bar convolved with u, where u is the input signal, where star represents the convolution operation. This is a key result that is saying that the kth sequence or kth token in the output sequence is nothing but the convolution product between the input sequence u and a fixed kernel k bar, which is defined, which is given by this particular equation, which is a function of the model parameters. Which means that if one computes this kernel k bar, then finding out the output is nothing but convolving whatever given input is with this pre-computed kernel k bar. So once the kernel is computed, one can do an inference on any of the input by simply taking convolution product between the fixed kernel and the given input u. Okay. Now this k bar is called the SSM convolutional kernel, SSM convolutional kernel or filter. Okay. Now one can guess what is the size of this filter. The size of the filter or the kernel is the same as that of the input sequence. When input sequence, if the input sequence is of length capital L, then the kernel is also of length capital L. Okay, so it's a pretty big filter, very large filter that we are talking about. Now the whole point of getting into an alternative framework to transformers was to see if we can handle longer sequence with computational ease. Now, what is the point of representing the output sequence in an SSM in terms of convolution is that from the signal processing principles, one knows that convolution in the so-called time domain or the sequence domain is equivalent to multiplication in the frequency domain. Okay. Now, because that is a possibility, and there are faster algorithms to convert a sequence into frequency domain, and these algorithms are called the fast Fourier transform algorithms. The whole idea in the SSM literature is to compute this kernel by taking it into the frequency domain and computing the output in the frequency domain via a multiplication operation in the frequency domain and converting back the output from the frequency domain to the sequence or the time domain via inverse Fourier transform. Now, since Fourier transform and inverse Fourier transforms are operations that can be done in logarithm time using fast Fourier transform FFT algorithms, it is considered to be faster compared to quadratic computation in transformers. That is the whole, the fundamental idea behind the state space models. Now, given that the goal is to compute this kernel k bar in frequency domain, so the rest of the discussion will be now around how would one compute this kernel k bar in an SSM setting. Okay, let us consider that computing. So before that, let's write that in practice, yk or the convolution is performed in the frequency domain using fast Fourier transform algorithms. Okay. Now, the next step is to come up with methods to compute the kernel k. So, computing the kernel k bar. In methods such as S4, which is one of the famous models from the family of state space models, the kernel is computed in the frequency domain using the generating functions. Now, why is it computed in the frequency domain? As we just saw before, the output or the state space model is implemented using the convolution operation, and convolution is equivalent to multiplication in the frequency domain. So the kernel itself is computed first in the frequency domain, and the signal is, or the sequence is multiplied with the computed kernel in the frequency domain, and the inverse transformers applied to get back to the sequence domain. So that is the operation that is done, and we saw that. Now, to compute the kernel, one needs to go to the frequency domain using the generating function approach. So what is the generative function? For people who are familiar with the signal processing literature, a generating function is typically some discrete transformation such as Z transform in its truncated version. Okay, so now recall that for k bar we had this k bar which was an L length real number that was given by c bar b bar, c bar a bar b bar, and c bar a bar to the power of L minus 1 times b bar. So we just saw that in the definition of k bar, right? How did we get that? We started with the definition of the state space models, which was given by these equations. Then we unrolled the equations and we obtained a recurrence, and we showed that that recurrence after unrolling can be written in terms of convolution between the input sequence u and a fixed kernel k bar, right? So whose expression is given by this particular equation. Now, to compute that in the frequency domain, we'll have to first compute the generating function or the Z transformation, truncated Z transformation for that. How do we do that? Let's call that k hat L of Z, that is given by summation of ki times z power I, where I equal to I runs from 0 to L minus 1. What is ki? Ki is the ith element of this kernel in the time domain, and we know that from this expression it is given by c bar a bar to the power of I times b bar. Okay, and therefore it just plug this ki in to this truncated generating function equation will get us to this particular equation where k cap L of z is given by the sum of c bar a bar to the power of I times b bar into z power I. So note that z here is the complex number that defines the transformation, the Fourier transform that we are looking at. To actually obtain the Fourier transform, once the entire generating function is computed, one needs to evaluate this entire thing at the roots of unity, right? That is how one navigates from Z transform to Fourier transform. Okay, so now if you look at this expression, the dependence of this of these terms on I is only through A and Z. Therefore, C bar can be taken out and B bar can be taken out. So taking C bar to the left and B bar to the right, we can write this generating function as C bar times this entire summation times B bar at the outside of the expression. Okay, now why did we do that? Let us only consider this particular expression. So consider this expression. The goal is to somehow get rid of the summation here and write it in terms of inverses instead of powers of a bar here. So that is the goal. So let us consider this particular expression, which is sum of a bar to the power of I times z power I, and this can be written in terms of these two expressions, that is I minus a bar to the power of L times z power L into I minus a bar times z inverse. So how did we get this? So this entire thing is a geometric series involving matrices and vectors. Okay, now there is something called matrix geometric series, and one can show that this summation converges to this particular expression if you have a matrix geometric series. I omit the proof here. Now it can also be shown that with large enough L, which means that if L approaches infinity, then this particular term which is there, which appears in the geometric series, approaches identity. Okay, therefore let's get back to what we were doing. So k bar of z, which is the generating function of the kernel, is now given, which was given by this particular expression. What did we do? We just took every term that was not dependent on I outside of the summation, and using the formula for matrix geometric series, we wrote down this sum in terms of inverses of inverses of these two matrices, and for L going to infinity, this entire term is identity. Therefore, the kernel, the truncated generating function of the kernel, is given by this particular expression, which is C bar times I minus A bar Z inverse times B bar. Therefore, the final expression that is given for the kernel, the generating function or the Z transform of the kernel is this particular thing, which is C bar times I minus A bar Z inverse times B bar. So, what is to be computed is this particular expression. Okay. Now, this particular expression also is not trivial to be computed. Therefore, what different models do is they impose a particular structure on A, which means that so far we have not said, we have not taken A to be having any particular form. For instance, A can be diagonal or A can be low rank or anything. We did not choose any of such kind of special structures on A, but different methods impose different kinds of structures on A to make this kernel computation tractable. Okay, so there are two special cases that we will study in this particular module. One special case is when A bar becomes diagonal. And by the way, when one imposes a particular structure on this A matrix, this method would be called structured state space models. And S4, the name S4 is derived from this particular method, which stands for structured state space for sequence modeling. Since there are 4 S alphabets here, now this thing is called S4. Okay, so the broad idea of most of the modern day state space models is to impose a particular type of structure on this A matrix and use different tricks of computation, different tricks for computing or estimating this A matrix and therefore the final state space model. Okay, so we look at some of the structures that can be imposed on this A matrix. The first thing is where A bar, A or rather A bar becomes diagonal. Now if A bar becomes a diagonal matrix lambda, what we have is that we have n diagonal elements. So typically A would be an n by n matrix. So we'll have n diagonal elements for this A bar matrix. With this, so look at this term that we have in the Z transform or the generating function of K. So what is to be seen is when one applies a particular structure on this A bar, how would this term morph is the question that we should be asking. So with A being diagonal, if one needs to compute this I minus A bar times Z to the inverse of I minus A bar times Z, then it is very simple to show that this would be diagonal of 1 by 1 minus lambda 1 times Z, 1 by 1 minus lambda 2 times Z and so on, where lambda 1, lambda 2 are the elements of the matrix A bar. Okay, so with this, if you just pre-multiply this thing with this expression with C bar and post-multiply it with B bar, then it is very easy to show that this entire thing can be written in terms of a summation of different scalar elements. The summation contains the elements of C, elements of B and 1 minus the elements of I minus A bar Z matrix. Okay. Therefore, the final kernel, the truncated kernel, for the case where A bar is a diagonal matrix, assumes this particular form. Now, why is this of importance? This is of importance because when A becomes diagonal, what involved powers of A? If you recall, the kernel here, let me just show you that. When we started, the kernel involved computing powers of A, right? So, matrix multiplication, computing the powers of matrix is a non-trivial operation. So, now with this particular structure assumption that was made on A, there is no computation of powers of A anymore. So, because then all you need to do is compute these terms. These are also called Cauchy kernels. It's very easy to compute these terms and these can be computed and therefore the kernel can be computed, and when the kernel is computed, one needs to just multiply that with the Fourier transform of the input signal to obtain the output and then invert the Fourier transform and take it to the sequence domain to obtain the output. That's easy to do. This is the key observation, that if a particular structure is imposed on the A matrix or A bar matrix that appears in the state space models, then computing this particular kernel in the frequency domain using the truncated generating function will become very easy. So that's the broad observation. Now, making A bar to be diagonal is too restrictive, right? So, a more general case is when A bar is not diagonal, but it is made the sum of diagonal and a low rank matrix. Okay, so this particular structure is called diagonal plus low rank. I mean, of course, there is a minus here, since negative sign can be seen as generalized addition. So this is called diagonal plus low rank, or DPLR in short. So what we have is A or A bar is imposed this particular structure where there is a diagonal matrix and there is a low rank. There are the outer product of two low rank matrices. Here P and Q are rank 1 matrices and P and Q are also learnable. Rank 1 matrices that are learnable. Okay, that are learnable. Now A bar is called diagonal plus low rank matrix. Now with this we need to again compute this particular expression I minus lambda z inverse, I minus A bar z inverse. Now instead of A bar being lambda diagonal matrix, now we have A bar to be having this particular form, which is diagonal plus low rank. I will skip the algebra, as I mean anyone who is interested can refer to the S4 paper itself. Now skipping the algebra, what one can show is that there's something called Woodbury identity that would help you to invert these sorts of diagonal plus low rank matrices. If Woodbury identity is applied and after algebraic manipulations, what can be shown is that the final kernel function that is obtained will have this sort of a structure. So it looks a little complicated, but it is not. What can be shown is that it is simply a linear combination of several Cauchy kernels, where each Cauchy kernel is given by this particular form, where you have a summation of different elements of C and B divided by some function of Z, which is the transform variable, and the element of the diagonal part of the matrix. That's it. Which means that in the entire kernel computation, there is no involvement of any powers of A. All we need to do is compute these kinds of terms, which are called Cauchy kernels, which involve element-wise multiplication of scalars and division with some other scalar, that is the element of matrix A. Okay, so this is what is done in S4, which is one of the earlier models of state space model family that were used for large scale sequence modeling. The other thing that is to be noted in S4 is that the A matrix or the A bar matrix is not initialized to a random matrix, rather it is initialized to be a special matrix called the Hippo matrix. So it was empirically shown that this particular structure of Hippo matrix leads to better generalization, and therefore A or A bar matrix is initialized to Hippo matrix. So that's the summary of what is done in S4, which is a special case of the state space model. Let me just recall quickly what was done. So discretized state space model has this particular form, and if for training and inferencing SSMs, what is to be done is, when you unroll the equations of SSMs, you get the output to be the convolutional product of a fixed kernel function with the input. During training, this kernel is not computed in the time domain because it involves powers of A or A bar. Rather, this is computed in the frequency domain. How is it computed in the frequency domain? Is via what is called as truncated generating function, or Z transform. The Z transform of this particular kernel is computed, and using the geometric series of matrices that will boil down to having this particular form, where you have C bar times identity minus A bar Z inverse times B bar. Now even this cannot be computed easily unless you impose particular structures on A. Now several structures can be imposed on A. One such structure is to make A bar to be a completely diagonal matrix. If it's made a diagonal matrix, then the kernel that is computed in the frequency domain has this form of Cauchy kernel, where there is some constant divided by 1 minus lambda I times Z. A diagonal case is very restrictive. To make it more general, instead of making A bar diagonal, one can make it a sum of diagonal matrix and low rank matrices. It's called diagonal plus low rank matrices. And using some matrix algebra tricks, what can be shown is this again the kernel happens to be a linear combination of multiple Cauchy kernel terms, where each of the Cauchy kernel terms has this particular form where you multiply scalars and divide by some function of z subtracted with the diagonal elements of A. Okay, this constitutes the SSM layer or S4 layer that can be used in any neural network. Now, so far what we have seen is that all the analysis that we did was with consideration that the input and the output variables are unidimensional. Now, for multidimensional data, which is the case in practice, SSMs are applied dimensions wise, which means each dimension of data is processed separately using one SSM, so one state space model, which is unidimensional. So just like we do multi-hit attention in an attention based transformer, where the input data dimensions are split into several short vectors, here an extreme case of that is considered, where every dimension of the data is separately processed using a different state space model. Please note that in this particular instantiation of the state space model, which is called S4, there is no dependence of ABCD matrices on time, which means that ABCD matrices are shared across the temporal dimension, even though they are different. We use different state space models for each of the data dimension, spatial dimension. In the temporal dimension, these ABC matrices are kept the constant across every time instant. Okay, so this is how one would implement, or one would rather approach the sequence modeling problem using a state space model. Every dimension is handled separately, and for each dimension one can have one SSM, and several SSMs can be stacked serially through the depth of a neural network, so to speak. So now this is how an SSM is implemented, and of course once the sequence models are constructed, there is an input and an output. You can use any of the loss functions such as root mean squared error or the cross entropy, and use gradient descent to update the parameters of the state space model. Let me write that. Training is via the usual empirical risk minimization. Using some loss function. So it can be done in both supervised and unsupervised way. If it's if you have supervised data, supervised losses can be used. If the labels are not present, if it has to be done in an unsupervised way, then just like the training of transformers are done by having a next token prediction task, right, which is the idea of masked language modeling, exactly the same thing can be done using an SSM as well. Okay. One other member in this family of state space models that we will discuss is what is known as MAMBA. It's also called as selective state space models. That's a more appropriate naming in my opinion. So in the model that we saw so far, which is called the S4, what happens is the kernel kernel is fixed, right? So kernel is fixed. So this happens because the model parameters which are the ABC parameters do not vary across time. I just mentioned that don't vary with time. Okay, so this is a known drawback for the of the S4 model, that the kernel is fixed because the model parameters don't vary with time. So what is the issue with this? So this implies that simple tasks such as selective copying cannot be accomplished using S4. Cannot accomplish with S4. So what is selective copying? Let's say that we have a particular sequence and the task is to selectively copy a particular subset of tokens from that particular sequence that belong to a predefined category. Let's say that you are given an English sentence. All we need to do is pick the words that correspond to noun. So this task is very difficult to accomplish with S4 because the model does not have any idea about different positions of different occurrence of tokens in a sequence. So this happens because all the parameters, these A, B, C, D parameters, are not a function of time. So to solve this, what Mamba does is to solve the above problem. So Mamba makes the parameters time dependent. Now this is the biggest difference between S4 and Mamba. In most of the state space models that came before Mamba, in all of them the parameters of the model were kept fixed across time, but in Mamba these are made functions of time. So therefore mathematically the model looks this. So x k plus 1 is a times a of uk, a of uk times xk plus b of uk times uk, and yk is equal to c of uk times xk. Now what is to be noted here is a, b and c are functions of input, functions of the input sequence. UK. So this is the biggest difference between S4 and Mamba model. Now there is a consequence of, and while this is a very good idea in the sense that the model parameters depends on the input, it also comes with some drawbacks in the sense that the above formulation does not lead to kernel computation unlike S4. So in S4 we had a fixed kernel, and that kernel could be computed because the parameters A, B, C were fixed and unrolling is possible, and when we unrolled we got a kernel that is a function of A, B and C. But here that cannot happen because A, B and C, these are functions of UK, therefore one cannot unroll them and cannot recurse, because at every time the A matrix is different, C matrix is different and B matrix is different. Therefore, unlike S4 where kernel was fixed and all the tricks that we saw, we just taking it to frequency domain and computing it using Cauchy kernel, is not applicable in terms of, in the case of a selective state space model such as Mamba. Then the entire computation differs here. Therefore, the model training and inference are not done in the frequency domain, unlike in S4. Frequency domain, rather they are computed in the time domain or in the sequence domain, sequence or time domain itself, using via faster parallel scan algorithms. So the authors of Mamba proposes algorithms which make the computation of this operation called parallel scan quicker. So what can be shown is that the definition of this particular state space model is very similar to computing what is called as the prefix sum. So what is prefix sum? In algorithms, one would know that given a particular sequence, you have, one would compute another sequence whose elements are cumulative sums of the previous sequence at every time. So that's called prefix sum, right? So what can be shown is that this particular type of state space equation, though do not adhere to the classical recurrence, it is very similar to the prefix sum operation, which can be made parallel using several parallel scan algorithms. So that is the idea behind making the Mamba faster. Otherwise this will become computationally heavy. To avoid that, several parallel scan algorithms are used, which are nothing but parallelization of this idea of prefix sum. So that's one thing. In Mamba, there are some hardware related tweaks that are also incorporated, which is that they are specially designed for some GPU architectures that would have multiple levels of RAM. And in Mamba, there's a trick called kernel fusion that is incorporated, where communication between the different types of RAMs in a GPU are optimized for speed. So I'll not go into details of all those techniques in this particular course. So the fundamental difference between S4 or other state space models and Mamba is that in Mamba, the parameters of the state space model A, B and C are made a function of time, and this enables several tasks that were not possible with the conventional state space models. And just like the case of a conventional state space model, Mamba is also applied independently across each of the dimension of data. So there will be as many Mamba blocks as there are the model dimension or the data dimension. Okay, so that takes us to the end of what I wanted to discuss with respect to the SSM state space models. And also that brings us to the end of this particular course, where we looked at several mathematical details of multiple state-of-the-art generative models, starting from adversarial networks, and we looked at variational divergence minimization, and we looked at variational autoencoders, diffusion models, autoregressive models, transformers, and now some introduction to state space models. With this, we come to the end of the course, and I wish and hope that this course was useful both in terms of theory and practical implications. And as I've been mentioning, one of the primary objectives of this course is to ensure that the students would appreciate and understand the underlying mathematical details of all these generative models, and equip students with the capability of independently going through research papers, understanding them, and possibly contributing new ideas to the field. I wish you all the best. Thank you.